This episode is brought to you by Brilliant. Rotational motion quite literally drives our lives. It's the most prevalent and oldest form of power transmission, and while it's obvious how it works, one of the more revolutionary yet nuanced evolutions of the concept has been the seamless redirecting of rotational motion, decoupling the orientation of the power source from the orientation of the work. Torque by nature wants to travel in a straight line. Reliably bending that force around the corner is a deceptive challenge. These are the machine elements that allow us to transmit power through a right angle. The first known conceptualization of right-angle drives were engineering descriptions made by 1st century BC Roman architect and engineer Marcus Vitruvius Polio. Vitruvius had documented that the transition from the inefficient simplicity of hand-cranked machines to the use of continuous rotary power of river water-driven wheels created a need for transmitting the generated horizontal axis rotation to the vertical axis-based millstones that utilized gravity for grain feeding. The solution was the first known right-angle gear drive that used a pin and face design. The Vitruvian mechanism operates on two orthogonal components, a vertical face wheel and a horizontal lantern pinion. The face wheel consists of a wooden disc mounted onto the water wheel axle with pegs protruding perpendicular to the face, while the lantern pinion is formed from an interfacing cylindrical cage consisting of two parallel discs connected by vertical staves. Mechanically, this system was more of an impulse drive than a true conjugate gear drive, as the face wheel's pegs struck the staves of the lantern pinion. The contact dynamics were dominated by sliding friction, sliding along the stave's length while pushing it, creating significant wear and heat. To mitigate this, woods such as holly or oak soaked in animal tallow were used to improve lubricity. Still, the axis independence and modularity of the Vitruvian mechanism made the watermill the predominant source of power for civilization for over 1500 years. By the Middle Ages, power requirements scaled from simple grain milling to the higher loads of sawing and hammering mechanisms. Millwrights realized that the friction of the face wheel pegs sliding against the lantern stave was the system's limiting factor and began to fit the staves loosely in their sockets between the two discs, acting as a primitive roller bearing. This helped distribute the wear around the entire circumference of the stave. While this helped with friction, the forces at the points of contact transmitted as abrupt, short bursts that produced vibration. From this limitation, a new approach would be developed based on the cog. These cogs were created by using wedge-shaped blocks of wood driven into mortises on the rim of a wheel. What made the idea so innovative was that the tapered shape allowed for smoother entry into the pinion. Because of the imprecise nature of wooden cogs, the depth of the interface was limited to prevent jamming during the approach phase of the mesh. This geometry inadvertently created recess action, where the majority of the drive occurs as the tooth is exiting the mesh. This action is smoother and less prone to vibration due to the rolling and pulling action, and it also prevents the destructive compressive locking of wooden teeth under heavy shock loads. The Industrial Revolution would mark a milestone in right-angled power transmission with the introduction of steam power. Steam generated torque at orders of magnitude higher than water wheels, and wood simply could not transmit this power without deflection or failure. For the first time, metals were used in these drives, with great cast iron specifically providing the necessary stiffness, though this came with a new range of design challenges. Early iron gears were cast from wooden patterns, and due to uneven cooling contraction and sand mold irregularities, cog size and spacing errors were common. When two iron gears are meshed, a single high spot or a pitch error would take the entire load, causing shock loading, and could fracture the brittle iron teeth. To address this lack of precision, the mortise construction technique would be adopted. In this approach, the iron rim was casted with slots in which wooden cogs were driven and keyed, with the wooden teeth meshing with a smaller all-iron pinion. The wood allowed the teeth to deform slightly, absorbing the impact energy caused by pitch errors, and it would eventually wear into a suitable contact shape as the meshed interface broke in. It also offered the secondary benefit of being a sacrificial damper, significantly reducing noise and protecting the machine frame from the resonant vibration of iron-on-iron gears at speed. With the ability to cast complex iron shapes, the 18th century also saw the introduction of pitch-cone theory. Face wheel-based mechanisms were geometrically approximate designs that inherently caused sliding and velocity variations across the tooth width from the 90-degree meshing of pegs. In pitch-cone theory, this limitation is removed by replacing the cylinders with cones with projected apexes that intersect at the exact point where the shafts intersect. This conical geometry ensures that the speed of the driving gear matches the speed of the driven gear at every point along the tooth, from the heel to the toe. In effect, this created line contact rather than point contact, allowing the load to be distributed across the entire width of the tooth, increasing power transmission capacity. The shift to iron gears also created a need for more system-level rigidity. Unlike wooden gears, which could tolerate misalignment, iron gears required the cone apexes to coincide perfectly. This forced the evolution of the machine frame from timber framing to rigid cast iron bed plates, with the gear drive now dictating the architecture of the entire machine. By the mid-19th century, the crude wedge-shaped gear teeth of existing designs were becoming a limiting factor for operating speeds. In order to reach higher rotational speeds without self-destruction, fully metal gears with mathematically perfect profiles were required. In 1874, a breakthrough in industrial gear production would become a big part in pushing past this limitation with the invention of the first Bevel gear planer by machinist and toolmaker William Gleason. What made Gleason's planer so revolutionary was in how it approaches the kinematics of cutting. Previous attempts at cone gear tooth cutting used cutters shaped like the tooth gap. This fixed shape, however, is geometrically flawed for bevel gears because the tooth gap tapers from heel to toe. Gleason's approach was to recreate the kinematics of the gear mesh itself in order to generate the tooth profile through coordinated motion. The machine mechanically simulated the gear rolling against a theoretical crown gear, using a straight-edged cutting tool that reciprocated towards the cone center, while the gear blank and tool holder rotated in a synchronized rolling action. This allowed the simple straight cutting tool to carve an octoid profile, a geometry that is an approximation of a spherical involute, the theoretical ideal tooth profile for a bevel gear. This manufacturing breakthrough allowed bevel gears to operate at thousands of RPM and would become a critical prerequisite for the proliferation of the internal combustion engine and the large spectrum of drivetrains across all forms of transportation that would be developed throughout the 20th century. With the development of right-angle drives, accelerated by the rise of the automobile, a new constraint on gear design began to emerge. Straight bevel gears engage the entire tooth face at once, creating a subtle impact event that produces a characteristic whine. This quickly became unacceptable as noise, vibration, and harshness, or NVH, became a factor in vehicle design, particularly as cars got faster. In 1913, Gleason's company, Gleason Works, would introduce a manufacturing process for a quieter type of bevel gear based on spiral teeth. The geometry of spiral bevel gears fundamentally changed the load transfer dynamics of a drive to one of gradual engagement. Teeth engage at one corner and the contact patch sweeps across the face rather than striking the full face instantly. The spiral angle ensures that before one pair of teeth leaves the mesh, the next pair has already entered, effectively pushing the average number of tooth pairs in contact or the contact ratio past 1, with contact ratios between 1.2 to 2 being preferred. Beyond smooth and quiet operation, spiral gears offer higher torque capacity and increased durability due to better stress distribution and reduced heat generation. While highly effective, the spiral geometry has the side effect of behaving like a screw thread, creating axial thrust, a strong force that pushes the gears out of mesh. To counter this, robust thrust bearings, such as tapered roller bearings and stiffer gear housings, are employed to prevent deflection under load. By the 1920s, automotive designers sought to lower the vehicle's center of gravity for both handling, interior room, and styling. However, the drive shaft running from the transmission to the center of the rear axle proved to be a limiting factor for floor height. The first production solution to this problem would be introduced by Packard in 1926 as the Hypoid gear. Based on developments made by Gleason Works and Swiss engineer Ernest Wildhaber, the Hypoid gear features an offset pinion axis with a mesh that is based on a revolved hyperboloid, a quadratic geometry resembling a warped cone. Because of this off-axis pinion placement, a larger diameter pinion with more contact area is typically used, with the spiral angle of the pinion being larger than that of the crown gear. This results in hypoid gears having much higher torque capacity than spiral bevels due to multiple teeth transferring force simultaneously. They also operate quietly and can be used for higher reduction ratios, all within a smaller package than that of a spiral-based drive. However, unlike spiral bevels, which mostly roll, hypoid teeth slide lengthwise across each other under high pressure, reducing mechanical efficiency. The pinion offset directly determines this mechanical efficiency, with larger offsets reducing it, though this comes with increased torque capacity. Specialized gear oils are required for hypoid gears due to the extreme pressure between the teeth created by the sliding action. These extreme pressure lubricants employ additives that react with the steel surface under the heat of friction to form a sacrificial chemical layer of iron sulfide that prevents metal-to-metal welding. While the automotive industry pursued right-angle drives that focused on speed and efficiency, a parallel development was occurring in the world of heavy industry with worm drives. Worm drives are based on the ancient concept of a screw meshing with a wheel. While it is generally attributed with the works of Archimedes, the Industrial Revolution would revive the concept into a truly practical mechanism, as the need for right-angle drives that could achieve massive speed reduction in a compact space were needed. Unlike standard gear pairs where a smaller gear drives a larger one, the worm drive features a screw or worm that has a continuous helix rather than distinct teeth. This geometry allows for larger reduction ratios, easily achieving ratios in the range of 50:1 to 100:1, all within a single simple stage. A single revolution of an input shaft may only advance the output gear by only one tooth. A significant side effect of the geometry of worm drives is a physical phenomenon known as self-locking. This occurs because of the low lead angle of the worm's thread, which causes the friction between the surfaces to become the dominant force. While the input shaft can easily turn the gear, if the load tries to turn the output gear, the friction clamps the system tight. This self-locking property acts as a built-in passive brake and eliminates the need for complex external braking mechanisms in safety-critical applications such as elevators and lifting equipment. While worm drives have high sliding contact and generate significant heat, this lower drive efficiency is accepted when considering their compact means of substantially decreasing speed and increasing torque. They work well in industrial machinery when paired with small electric motors that are generally high speed and low torque. They can even be configured as high-precision duplex drives with adjustable backlash. While worm gear drives have been used in some vehicle drivetrains to provide ground clearance and self-locking drive systems, its inherent inefficiency and high heat generation eventually relegated to specialized roles. Today, the drivetrain application of the mechanism is predominantly found in industrial haulers and on torsion systems, where the worm gear's friction properties are adapted for torque management. As the aviation industry expanded in complexity during the 1930s, the axial thrust produced by spiral gears were creating a need for unacceptably heavy housings, and straight bevel gears were simply too weak to replace spiral gears. Gleason works would once again solve the problem with the development of the Zerol gear. This design serves as a hybrid solution, featuring curved teeth, which provide the high strength of a spiral gear. However, the teeth are cut with a spiral angle of 0 degrees. This specific geometry mimics the load path of a straight bevel gear, generating minimal axial thrust, reducing stresses on the housing and allowing them to be made lighter. With lighter housings, flexing under load becomes an issue. Gleason addressed this on Zerol gears by using a technique originally developed for the spiral bevel cutting process called crowning, where a slight convexity is ground onto the tooth surface. When the housing flexes and the gear tilts, the contact point shifts but remains on the thick, strong center portion of the tooth, never reaching the fragile edges, allowing the gear to maintain its performance even when the housing flexes. In the aviation world, rotary aircraft introduced its own set of challenges as their drivetrains formed some of the most demanding right-angle drives. By the 1960s, transmissions had to contend with converting the high-speed output of a turboshaft engine to the lower-speed main rotor, which could handle thousands of horsepower all without excessive weight. These drive systems also had to deal with thermal expansion and flex that shifts the contact pattern. As heavy, ultra-rigid housings started to become impractical, the face gear split torque transmission underwent development in the 1970s as a solution. In this system, a disc-shaped face gear geometry is driven by cylindrical spur pinions. What gave this configuration a technical advantage is the spur pinion's axial freedom. Unlike a bevel pinion, which must be locked in place, the spur pinion in a face gear set can float along its axis without disturbing the mesh quality. This floating capability is the key to the system's distinct advantage, passive torque splitting. When the input pinion is sandwiched between two opposing face gears, it is allowed to float axially along its own center line. When the engine applies power, the pinion pushes against both face gears simultaneously. If one face gear offers slightly more resistance than the other, the pinion will physically slide away until the forces on the top and bottom are perfectly identical. This creates a mechanical equilibrium where the torque split is exactly 50-50 between two load paths. This happens instantaneously and passively, without the need for sensors, hydraulics, or computer control, effectively halving the stress on each gear tooth. In modern high-powered twin-engine helicopters, this architecture scales up into a concentric split torque system. A second engine is interfaced through a second floating input pinion at a different point around the perimeter of the same face gear sandwich. Both engines drive the same pair of upper and lower face gears, and both input pinions independently float to balance their own torque loads. The rotational power from the two face gears is then recombined through idler gears and a large central bull gear to spin the main rotor blades. The tail rotor drive is integrated as a simple power takeoff. Because the large face gears are spinning at a precise reduced speed, a separate output pinion can simply be meshed against one of the face gears. Because of the displacement insensitivity and load sharing characteristics of these systems, they can be made lighter and less robust, though this comes at the cost of complexity of manufacturing. It was only the advent of modern multi-axis CNC grinding that allowed for the precise generation of these complex surfaces on hardened steels. Beyond these right-angle drives, there is a fascinating world of exotic alternatives designed for highly specific use cases. Even the future of conventional right-angle drives will see algorithmic topology optimizations paired with additive manufacturing that remove material not carrying a load, creating new variations of proven concepts and likely bringing about yet another revolution in how we transmit power orthogonally. Silent high-load right-angle drives fundamentally distill down to a thorough understanding of contact geometry, where theoretical ideal curves collide with the realities of thermal expansion, material properties, and deflection. If you want to build a level of geometric understanding that helps you analyze and optimize components in a similar manner, you should check out Brilliant. Brilliant is an incredible way to master math, computer science, and engineering because it focuses on helping you truly understand the concepts rather than just memorizing them. It builds on the belief that you are a problem solver. You just need the right tools to unlock that potential. Instead of sitting through passive lectures, you learn through interactive hands-on challenges that get you to those breakthroughs in understanding. And with their new larger content library and personalized practice sets that adapt to your progress, you'll always be challenged at exactly the right level to keep you growing. You will also be confident that you're learning the right way because Brilliant is handcrafted by an award-winning team of teachers, researchers, and professionals from MIT, Harvard, Google, and more, harnessing that expertise to design personalized practice sets just for you. And speaking of geometry, I highly recommend checking out Brilliant's Coordinate Geometry course. It teaches you how to form and analyze geometric connections through mathematical relationships, building a critical skill in design. To start reaching your serious learning goals, go to brilliant.org/newmind or scan the QR code on the screen. That link will let you learn for free on Brilliant for a full 30 days. Brilliant is also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything they have to offer.
I had to run a wire through here, but it required a lot of weird drilling. So I got this right angle attachment, but one wasn't enough. I needed at least 8 more. Now I can drill with no problem.